Oh, hey there, didn't see ya. I was just about to talk about my Lab 5 results. Why don't you join me? So Lab 5 explored how to correct the power factor of a circuit containing inductors, and proving this correction worked by calculating the complex power in both the original and corrected circuits analytically, digitally, and physically. I will know whether my power factor correction was done correctly if the complex power for all three of my calculations agree, and the complex power of my corrected circuit has an imaginary value of 0. To find the value of the capacitor needed to correct the imaginary load caused by the inductor, I calculated the load's network equivalent resistance, the voltage source's RMS value, and the RMS current. I then used these values to calculate the complex power. The power factor was then calculated to ensure it had a value that was less than 0.9. Afterwards, the sum of the capacitor admittance and inductor admittance was equated to 0. This equation was then rearranged to calculate the capacitance needed to make this equation true, and a new circuit was created with the capacitor in parallel to the load with this capacitance. To check to see if this process worked, the complex power of both circuits were calculated analytically by calculating their equivalent resistances and using this to calculate the voltage across and current through them using voltage dividers and Ohm's law. Lastly, their complex powers were calculated by multiplying the voltage by the conjugate of the current, all divided by 2. The imaginary part of the complex power of the corrected load was checked to see if it equated to 0. And it did! Yay! Next, their complex powers were derived digitally by creating both circuits in Multisim and hooking them up to a digital Tektronix oscilloscope before and after the load network. The voltage through each load network was calculated by converting the time difference between the two voltage outputs on the oscilloscope into the angular difference and plugging this angle into the time domain equation of sinusoidal voltage. The voltage across the loads was calculated by subtracting the voltage after the load from the voltage before the load. The current through the loads were derived using Ohm's law by dividing the voltage across the loads by the load's equivalent resistance. Lastly, their complex powers were calculated by multiplying the voltage across them by the conjugate of the current through them, all divided by 2. To confirm that this worked, all the calculated values were compared to the analytically derived values to see if they were consistent. And they were! Double yay! Finally, both circuits' complex powers were derived physically by physically building them and using a physical oscilloscope to measure the voltages before and after the load network. The voltage across, current through, and complex power of these circuits were then analytically calculated using the recorded values in the same way they were calculated digitally, except for the current, which was calculated using Ohm's law by dividing the current measured after the load by the transmission resistance. The error propagation equation was then used to calculate the acceptable range of the physical results. All the calculated values were then compared to the values determined digitally and analytically to see if the three methods had been completed correctly. For the most part, the values were consistent, almost AAA. The imaginary part of the complex power of the corrected circuit was 0 for all three methods. This means that all three methods were conducted properly, and the capacitance needed to correct the power factor of the original circuit was calculated correctly. This is a very important skill to have, as power companies charge based on apparent power, which does include the imaginary reactive power caused by a lag in the voltage due to the inductor. Therefore, by adding these capacitors in parallel with the inductive load network, large factories and even small appliances can save money spent on power by applying this skill. Thank you for joining me. Bye!